Dear students, I welcome you back to the fourth unit in the electromagnetic field subject. So the fourth unit is time varying fields and Maxwell's equations. So in the previous short video, I explained to you what is Faraday's law, how to derive Maxwell's second equation by using Faraday's law, then continuity current equation we have seen. In this lecture, we are going to see what is displacement current density concept. We'll see Maxwell's first equation, and also we'll see Maxwell's third equation and fourth equation. So as you can see here, what you're seeing here is a circuit where an AC voltage is given to a capacitor. So what happens when a AC voltage is given to a capacitor? It charges and discharges. Okay. So how does it happen? Because conduction current means when there has to be a continuous flow for the current to flow continuously in a circuit. The capacitor looks like an open circuit, doesn't it? Because the capacitor is an arrangement geometrically. It is designed such a way that two parallel plates are separated by a dielectric or air is there. So how come that conduction current? How can there be current conduction? So that is the question here. So, but if you connect, the capacitor is there. If there is still current flow in the circuit, the ammeter shows reading. So what is the reason for that? Is displacement current. So from the upper plate to the lower plate, the charges are displaced. The current conduction takes place. Okay, the displacement current density is given as JD is equal to dou D divided by dou T. So what happens to the time varying magnetic field that is created by the current that passes through the capacitor, C capacitor? So that is very well explained by this displacement current density. JD is equal to dou D divided by dou T, where D is electric flux density. Okay, so this displacement current density, we'll be seeing it shortly. It will be very useful for us to derive the Maxwell's first equation. So what you see here is Ampere's circuital law, which we have already seen, which we have already discussed in the third unit. So a steady current is flowing. So when the current is flowing, magnetic field is set up. So del cross H is equal to J, H dot dl is equal to Y. H dot dl line integral closed loop, or close to contour. H dot dl is equal to I. So del cross H is equal to what it actually tells. So when a current is flowing through a conductor, you calculate that a magnetic field around the conductor, you integrate it totally, it will be equal to the current which is flowing through the conductor. That is closed loop integral H dot dl is equal to I. The point form or differential form of Ampere's circuital law is given as del cross H is equal to J. Okay. Now see here, we'll see this. We have seen displacement current. With that, we are going to derive Maxwell's first equation. Del cross H is equal to J. This is Ampere's circuital law point form. This is 4.19. It is shown in the notes here. Del cross H is equal to J. Now vector identity. Take divergence on both the sides, that is del cross H is equal to you take divergence on both the sides across there is an identity that del cross H is equal to 0, because the magnetic field is rotating. Curl of divergence is 0, which is already divergence of a curl is 0, which is an identity that we already know. So according to this equation, this right hand side also becomes 0. So del dot J is also 0. So del cross H is equal to J. This is the equation taking divergence on both the sides. Because of this identity, del dot J also, the right hand side can also be equated to 0 and can be said that del dot J is equal to 0. But according to continuity current equation, we have derived that del dot J is equal to minus dou D divided by dou T. So we have seen this in the first lecture. Del dot J is equal to minus dou V divided by dou T. So this concept of displacement current is added here. So this J in the first equation, del cross H is equal to J. This J plus this JD term is displacement current density term is also added here. So which is equal to minus dou V divided by dou T. So that is Maxwell's first equation. This is Maxwell's third equation, which is derived. So as you can see here, this is Gauss law for electric field. What Gauss law tells: the electric flux lines coming out of a closed Gaussian surface or a closed surface will be equal to the number of charges that are enclosed inside, that are already there in the surface. So the surface integral del dot ds is equal to the charge enclosed. Taking divergence, by using divergence theorem, the surface integral d dot dl can be equated as del dot d dv, and if you write it like that, you will be getting volume integral del dot d dv is equal to volume integral q can be equated. Q, what is Q? Charge and charge density, volume charge density can be equated as Q is equal to volume integral rho v dv. So equating the two here, you will be getting volume integral del dot d dv is equal to volume integral rho v dv. Cancelling out the integration symbols, you can write del dot d is equal to rho v. This is Maxwell's equation, third equation. Maxwell's fourth equation is Gauss law for magnetic field, which is surface integral b dot ds is equal to 0. Because why do I write surface integral b dot ds is equal to b dot ds is equal to 0? Because magnetic fields cannot exist in isolation. As per the Gauss law, either it is a positive charge or a negative charge which is present inside a closed surface. The magnetic electric flux which is coming out will be equal to the total charge enclosed. But here you cannot, the case of non-existence of magnetic monopoles, because North Pole and South Pole cannot be separated. When you start breaking a magnet, it gets subdivided into a North Pole and South Pole. Even to the atomic level, when you break it, the North Pole and South Pole of the magnet still remains. So North Pole and South Pole cannot be separated. So when you apply Gauss law for magnetic field, the flux lines coming out, for the case of non-existence of magnetic monopoles, the flux density always remains 0 for a closed surface. So b dot ds is equal, surface integral b dot ds is equal to 0 can be written with the divergence theorem, can be equated and written in the form of a divergence theorem. So b dot ds can be written as del dot b with the help of divergence theorem. So del dot b becomes 0. This is the fourth equation of Maxwell's equation, which is derived from Gauss law for magnetic fields. So with this we will stop. Happy learning, students. Thank you.